If your vector search keeps returning old or duplicated chunks after document updates, the problem is not embeddings. It is your upsert and delete strategy. I will show a simple pgvector pattern you can copy in a few Python snippets. By the end, you will understand a repeatable pattern to upsert, gate updates by content hash, and tombstone deletions so your retriever stops serving stale chunks. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Vector databases are often used inside retrieval-augmented generation workflows to find relevant document chunks. The common pain is stale results. You update a document, but the search still returns the old text or returns duplicate chunks created by repeated processing. That breaks answers and confuses downstream chains. Success means the retriever always serves the most recent chunk and never hands back a removed piece. This pattern fits small to medium corpora, and it scales gracefully as you add an ANN layer later. At a high level, the idea is simple. Give each chunk a stable chunk identifier. Compute a content hash for the chunk text. Store both the embedding and the hash in the index. When you need to update, gate writes by the hash. When you delete, mark a tombstone and exclude tombstone rows from searches. That combination prevents duplicates and prevents stale hits. We will build a tiny toy flow you can lift into a RAG pipeline. You will first create a table and index, then insert two chunks, run a similarity query, perform an idempotent upsert guarded by content hash, and finally, tombstone and filter a chunk. The code uses PostgreSQL with pgvector and psycopg. Now we connect and create the index table. This snippet connects to PostgreSQL with pgvector using psycopg and creates an index table. It starts by opening a standard database connection and ensuring the pgvector extension exists. Then it creates a table with a stable chunk identity column, a content hash column, an embedding vector column, the chunk text, and a tombstone flag. The core idea is to make the schema explicit about identity and freshness. The index creation focuses on the embedding column, so similarity search is efficient. With this table, you have the fields needed to gate updates and to filter out deleted chunks at query time. Now we insert example chunks. This example inserts two chunks with stable chunk IDs and content hashes. It demonstrates creating two distinct chunk identifiers and computing a content hash for each chunk text, then inserting the chunk ID, the hash, the embedding, and the text into the index table. The snippet shows the simplest insert path where both rows are new. The important bit is the stable chunk ID and the content hash stored alongside the embedding. That record structure is what lets later steps detect unchanged content and avoid creating duplicates or unnecessary re-embeddings. Next, we run a similarity query against the index. This code runs a pgvector similarity search and returns the top chunk. It shows how to pass a query embedding and run a nearest neighbor search against the embedding column, selecting the single best row ordered by distance. The snippet retrieves the chunk ID, content, and distance for the top hint. The point here is to illustrate the retrieval contract. You get the most similar chunk according to the vector store. At this stage, the search does not yet consider content hash gating or tombstones, so it gives us a baseline of what the retriever would return from the existing rows. Now we make updates idempotent and safe. This snippet performs an idempotent upsert using a content hash gated on conflict. The core idea is to make an update conditional on the stored content hash so that identical content does not change the row. The snippet computes the new hash, then tries to insert. On conflict, It compares the incoming hash to the existing hash and only overwrites the embedding and content when the hash differs. That means repeated runs on the same text are no-ops. The practical knob here is the gating condition. If you gate strictly on the content hash, you minimize unnecessary writes. If you loosen that gate, you can force updates more often, but risk duplicates or redundant embedding work. Finally, we remove a chunk without losing history. This example tombstones a chunk and filters retrieval to avoid deleted results. It updates the row to set the tombstone flag true for the target chunk ID instead of deleting the row outright. The retrieval query then includes a condition to exclude tombstoned rows so they never show up in similarity results. The advantage is twofold. You retain an audit trail and you avoid race conditions where a concurrent query might see a deleted row. In a production pipeline, you can sweep old tombstones later to reclaim space, but tombstoning is the safe first step. In a real RAG system, you map document updates to content hashes and chunk IDs. When a document changes, you split into chunks, hash each chunk, upsert with the gated logic, and mark removed chunks as tombstoned. The retriever runs the same similarity query, but always filters out tombstones. That keeps answers current and avoids duplicates. Recap: it is a schema plus workflow that stores stable chunk IDs and content hashes. Use it when you need consistent, non-duplicated retrieval after document edits. One caveat: tombstones keep history and require a cleanup policy if storage matters. Next step: run experiments with an approximate nearest neighbor index in pgvector or an ANN layer, and measure recall and latency as your corpus grows. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.